Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Numerical Differentiation. Basic Concepts. Numerical differentiation refers to the process of approximating the derivative of any continuous or discrete function using numerical methods rather than obtaining it analytically, even if it is possible. The numerical differentiation is a useful and powerful tool for approximating derivatives when the function is complex, unknown, or when you only have discrete data points. The derivative of a function f(x) at a point x is approximated by using finite differences, which rely on the values of the function at nearby points to estimate the slope of the tangent line, i.e., the derivative, at the desired point. The values of a discrete function are represented by a number of distinct and separate data points that are unconnected to each other. Note that the following graphs depict discrete functions. A discrete data distribution represents situations where the data can only take on a finite or countable number of distinct values. In other words, the variables take on specific, distinct values rather than continuous values. The values are expressed by a table or list of ordered pairs, or points. The data derived or collected can be tabulated as in the following examples. Most physical properties, density, viscosity, heat capacity, enthalpy, saturation pressure, etc., are assumed to be smooth functions of space and time whose explicit mathematical relationships are not known. The physical properties of solids, liquids, or gases are generally available as discrete functions of temperature, pressure, etc. The properties of materials, describing physical, mechanical, thermal, electrical, optical, chemical, and so on, are mostly obtained experimentally. They are available in either XY or tabular data. Discrete functions are also encountered in the numerical solution of the differential equations. A discrete function may be either uniformly or non-uniformly spaced. Data collected, usually with digital instruments, are sampled at equal intervals, which gives uniformly spaced discrete data sets. While it is desirable to perform experiments for uniformly spaced variables, the analyst may be forced to obtain non-uniformly spaced data due to technical difficulties. Although an analytical function may be mathematically well-defined and differentiable, in many real-world problems, the true derivative of a function can be difficult to compute, especially if the function involves complex expressions or is not easily differentiable in a closed form. For example, the following function looks simple, but its first derivative involves long and complicated expressions. In this regard, numerical differentiation offers a simpler and more efficient way to estimate the derivative. The first derivative, or true slope, of y equals f(x) at x equals is the limit of the value of the difference quotient as the secant lines get closer and closer to being a tangent line. The derivative of a smooth, continuous univariate function, y equals f(x) at x equals a, is expressed as follows. This limit operation can be carried out if y equals f(x) is explicitly known. It is impossible to truly perform the limit operation for discrete functions. Thus, the numerical differentiation is always approximate, and the result naturally contains some error. Consider the function y equals fx and its tangent line at the point A, at x equals a and y equals fa. Using the point B at x equals a plus h, the slope of the secant line is obtained from the right triangle as follows. The slope of the secant line, MAB, passing through the point A and B, is not equal to the true slope of the tangent line. Next, we reduce the spacing between the 2 points by half. The abscissa of the point B' is a plus h over 2. The slope of the line passing through the points A and B' is found from the right triangle. Although the slope of the secant line from A to B' tends to approach the true slope, it is not yet equal. We further reduce the spacing between the points A and B' by half. The abscissa of the point B' is a plus h over 4. The slope of the line AB' approaches towards the true slope. Note that as h goes to 0, point B moves closer to point A along the curve, in which case, the slope of the secant line becomes identical to that of the true slope. If y equals fx is a continuous and infinitely differentiable function, it can be expanded into the Taylor series in the neighborhood of point A. Where Rn is the remainder defined as follows. Solving it for f'x, we obtain the following expression. As h goes to 0, all the terms except the first one go to 0. Neglecting the remaining terms that contain multiples of h to the k yields the approximate formula for the first derivative. The approximation error can be determined as follows, where the right-hand side is the total, or so-called the truncation error. However, it is impossible to estimate the true truncation error because the higher derivatives of f are also unknown. We are generally interested in knowing the relative magnitude of the error rather than its true value. Note that h to the power k terms, k greater than and equal to 2, vanish quickly so that we may write f'A in the leading error is unknown when fx is a discrete function. Thus, an upper bound on truncation error can be obtained by replacing f'A with f'C, where Xc is in between a and a plus h, and the absolute value of f'C denotes the maximum value on the interval from a to a plus h. Round-off error arises because the derivative of a function cannot be computed with the same precision as the function itself. The sum of the coefficients of the terms in the numerator of all difference formulas is 0, so when evaluating the numerator, several significant figures may be lost while performing multiplication, subtraction, and addition operations with coefficients. We cannot make h too large either because the truncation error would dominate the results. Adverse effects of round-off error may be mitigated to some extent by either using high-precision arithmetic or adopting finite difference formulas of accuracy greater than or equal to 2. To analyze loss of accuracy in numerical differentiation, let circumflex fx denote the floating point representation of a function value. The difference between the true and machine-computed derivative, circumflex f' computed x, of the forward difference formula is written as follows. Next, we assume circumflex fx differs from the true fx value, in relative error sense, by a small amount on the order of machine epsilon. Substituting floating point values of the function, we find the following. The first term denotes the truncation error, and the second term denotes the round-off error. We note that both errors depend on the magnitude of the spacing h, which allows us to write the total error as a function of h. Upper bound for the truncation error of the forward difference formula is linearly proportional to h, with m over 2 as the proportionality constant, where m is the maximum magnitude value of f double prime. This relation implies that as h goes to 0, the truncation error decreases linearly to 0, as depicted in the region labeled as truncation error. The upper bound for the round-off error becomes, assuming fx and fx plus h are equivalent, and epsilon 1 and epsilon 2. This expression can be reduced to the following, where n is the maximum magnitude value of f, but we do not know the signs of epsilon 1 and epsilon 2. Thus, we cannot estimate the absolute value of their difference accurately. If epsilon 1 and epsilon 2 have opposite signs, the magnitude of the difference could be doubled. We note that in the region dominated by round-off error, the error is inversely proportional to h. For large h, it is initially very small, but then increases for decreasing h. The total error decreases for decreasing h, but starts to increase as the round-off errors begin to dominate the computation. This outcome implies that there is an optimum value for h, where the total error is minimum, and we cannot reduce h to improve the difference approximation. For f'(x), we obtain the optimum value of h by setting the derivative of total error with respect to h to 0, which yields the following expression. Note that the optimum value is valid only for the first-order finite difference approximation we started out with. As we will see in this chapter, there are many more finite difference formulas that we use in our calculations. Thus, the optimum values of h for every approximation will naturally vary. Consider a uniformly spaced discrete function, y equals fx on x0 to xn. We adopt following shorthand notations. Using the shorthand notation, we may write the first derivative as follows, where delta operator is the forward difference operator defined as follows. We now consider the Taylor series of fxi minus h about xi. Solving for f'xi yields the following expression. Note that the truncation error is first order, thus we may also write this as follows, where nabla symbol is used as the backward difference operator. Finite difference expressions for higher-order derivatives can be developed in the same way using Taylor series expansions. The forward and backward difference formulas of the nth derivative of fx at x equals xi with the first order of accuracy are expressed as follows. It is possible to develop higher-order and more accurate finite difference formulas by simply including more terms, leading term, and so on, from the Taylor series expansion. We consider following first-order approximation. Replacing the second derivative with its first-order difference approximation yields the following. Collecting the common terms and simplifying gives the following difference approximation, which has a second-order truncation error. That is, truncation error is proportional with h squared. Or we may cast this approximation called forward difference formula in shorthand notation as follows. Similarly, we obtain a second-order approximation called backward difference approximation due to incorporating two backward points in the formulation. When dealing with a set of discrete data, we do not know whether the data is generated from a continuous or piecewise continuous function. The function, in fact, may not be differentiable at some points in its domain. Hence, numerical differentiation must always be handled with caution. Consider the Taylor series of fxi plus h and fxi minus h about xi. Subtracting the two series side by side, the derivatives of even degree cancel each other out. Solving for the first derivative, we find the following expression. Notice that the truncation error term is proportional to h squared, that is, the approximation is second order. In shorthand notation, we express it as the error term involves the maximum magnitude of the third derivative. Adding fxi plus h and fxi minus h side by side leads to solving for the second derivative gives the following finite difference approximation, which is referred to as central difference approximation. In shorthand notation, it leads to the following with the truncation error term, which is second order. More compact finite difference expressions can be obtained by incorporating the central difference operator delta, which is defined as follows. Then, we may write it in shorthand as follows. The graphical depiction of the data points used, along with the predicted slopes using the forward, backward, and central difference formulas for fx is presented in the figure. The estimated slope with the central difference formula is in better agreement with the true slope of the tangent line. If the number of data points is sufficient, the central difference formulas should be preferred due to their second-order accuracy. The advantages of the finite difference formulas are: finite difference formulas are simple and easy to use. Higher-order finite difference formulas can be easily generated using difference operators. For a given h, second- or fourth-order difference formulas offer a decent trade-off between accuracy and the number of function evaluations. Derivatives of explicit functions can be accurately computed by increasing the order of accuracy, i.e., data points. The disadvantages of the finite difference formulas are: the truncation error is a function of interval size, and it has a strong influence on the accuracy of differentiation. Difference formulas are plagued with round-off and loss of significance errors when h is very small. When high-order difference formulas are used, there is no need to use a very small h to get a very good estimate. However, such formulas avoid floating point problems at the expense of the increased number of function evaluations. That is all for now. See you next time with another topic. Bye.